I'm Alex White. I'm a math major here at Frostburg State University. My project name is the Pythagorean Theorem in 3 ways. So, the first way is Euclid's proof, and that sort of came about in the 300s BC. And so its sort of proof goes as follows. So we start with the triangle, and we append on each of the sides a square. And then we draw a line from that corner to that corner, from that corner to that corner, one straight down the middle, one from that corner to that corner, and again from that side to that side. And so we find that this triangle, when we move it up, half the area of that square, and that triangle, when we move it down, the area is half that rectangle. When we do a similar thing on the other side, sort of have the area of that triangle, move it up, double that area. Have another triangle, move that one down. I have half the area of that rectangle. And so you can see that the area of that square plus the area of that one is equal to that third one, which is just a squared plus b squared is equal to c squared, what you would normally see in a geometry class. The second proof is a generalization of the Pythagorean theorem. And this is from Pappus. He was a contemporary of Euclid, born around 290 BCE. So this one, we start with any other non-right triangle, and we append parallelograms to a set of squares. And we extend those two sides, draw 3 parallel lines, and we find that the area of those 2 parallelograms is the same. And we can just shift that one down, and the area of those 2 parallelograms is the same. Shift that one down, fade out the lines that we drew earlier, and we get the same figure that we had in the first one. The area of that parallelogram plus the area of that one is equal to the area of that third parallelogram. And that's true for any non-right triangle. So it's sort of interesting that you still have that same fact. Although the equation isn't quite as nice, you still have that same sort of fact you can use in that way. And the third one, probably the most interesting one, is a tiling proof. So we start again with the square, and we append on each of the sides a smaller square. And then we can sort of tile it up to the right. We can draw a third square. And we can sort of see we have the same similar shape there. And if we move that square over, we just get the Pythagorean identity yet again. And that one's sort of it's almost like magical. It sort of like fades out and shifts that way. But it's very interesting. There's sort of another way you can do it where you tile the whole plane with that sort of square with other 4 squares on it. And then you can sort of shift the grid such that you can get that same sort of shape with a square with the a squared, b squared, and c squared on it. So sort of the goal of my project was to just sort of show people sort of visual proofs in math, and that you can sort of use animations to help make sense of what would have normally have been just like a paragraph of text into something that's sort of visually and easy to digest during my math degree in history and mathematics.